learn the solution for sum of subsets problem using backtracking. So let us first try to understand what is the problem statement. So says that we are provided with a subset of positive integers. Let this subset be 3, 4, 6, 7, 9, 10 and 11. And along with this we are provided with a number m that is equal to 20. Now the problem is that we need to find all the subsets of the set S. Let it be named as S. We need to find all the subsets of the set S such that the sum of the elements of this subset equals to the positive integer m. So this is our problem statement. We need to find all the subsets summing to a positive integer m exactly. Okay, so for example, if we try to find some of the subsets which are the probable solution, then 3 plus 4 plus 6 means we cannot generate it. Fine. Next is if we pick 3, if we pick 7 and if we pick 10. So this is the probable solution. So one of the probable solution is 3, then 7 and then 10. So these are the three items whose sums is equal to 20. Fine. So let us try to name this given set as W. So W in this case was equal to 3, 4, 6, 7, 9, 10 and 11. Fine. And we need to find the subsets. So one of the subset which is a solution for this is 3, 7 and 10. So its representation can be in the form of a vector x which contains the elements from the sets 0 and 1. 0 means not included and 1 means included. So for this example or for this solution we included 3. It means x of 1 is going to be 1, then 4 was not included, 6 was not included, then 7 was included, then 9 was not included, then 10 was included and 11 was not included. So this is one of the solution for this sum of subsets problem. Try to generate more solutions. So the other solution may be the selection of this 9 and 11. Fine. So we may write it that the other solution for this problem is 0, 0, 0, then again 0, then 1, then 0, then 1. So this is the second solution, and in this way you may generate many solutions corresponding to a given set. Now let us discuss the possible solutions for this sum of subsets problem using backtracking. We all know that while solving any problem using backtracking we need to consider a solution space, and which is to be seen in the form of a state space tree, and then from the state space tree we need to reach to the answer nodes, answer states you may say. Fine. So this is the probable sequence of solving any problem using your backtracking approach. So first things that comes is the state space tree. So this problem can be solved in two ways. One is the fixed tuple solution and second one is the variable tuple solution. So we are going to look at them one by one. So this is the state space tree, or you can say solution space representation for variable tuple, for the variable tuple size. Which tuple? The solution tuple, variable tuple size, and this solution is for your fixed tuple size. One that I quoted in the example was falling under the fixed tuple size. This one. It means all the solutions being formed using this approach will be containing n number of items or n number of terms in this. Means the subset is going to have size equal to n. Fine. But the values of this subset are going to be from the set 0 and 1, where 0 was denoting absence and 1 was denoting presence. So this is the fixed tuple size solutions, and the second one is the variable tuple size solution. So let us try to discuss them one by one. Fine. So let us first go for the variable types tuple. So just try to assume that in this case n is equal to 4, means our initial subset was having which we considered as w1, w2, w3 and w4. 4 items were there. You may just name them as weights. Fine. So we need to choose the subsets which are summing to exactly m. Fine. Now one of the solution for this problem instance may be to start from the root, and then at the root we are having 4 options to choose: item number 1 first, item number 2 first, item number 3 first, or item number 4 first. So x1 may be item number 1, 2, 3 or 4 in this case. Fine. So if we choose the item number 1, then we reach to this node number 2, and at node number 2 we are having 2 options for x2, which are 2, 3 and 4. So this is 2, this is 3 and this is 4. If we followed this one, done, then we are having only 2 options. x3 will be having only 3 and 4 and so on. Fine. So this is the method that we followed in n queens problem also. When we tried placing queen number 1 at column number 1, then column 2, then column 3 and then column 4. Okay, so this is called as your variable tuple size state space tree or your solution space. And the nodes at which we reach to the conclusion that this node further is not going to generate any solution, then we just label them as B, or you can say backtrack B as B. Fine. So this is one of the method that is called as the variable tuple size. Why variable? Because at the end we are going to have x which may be containing x1, then x2, then x3, which may be containing x2, then x3, then x4. Fine. So this may be the solution, and which is variable in size, may be containing only one x, maybe containing 2 x's and so on. So the next one, that is the simpler one, is our fixed tuple size solution. Now the fixed tuple size says that we start from the root and we go for a check for the first item. It will be included or it will be excluded. So this is excluded, this is included. Fine. If it is included, then we follow this branch and we move to the second item. If we excluded, then we move at node number 3 and going to pursue from here. Now at node number 2, again we can include item number 2 or we can exclude item number 2. Fine. If we include it, then we move to 18. If we exclude it, then 19. And the same case when item number 3, include it or exclude it. Item number 4, include it or exclude it. Fine. So at the end, what exactly we are going to attain is a solution which will be containing 4 values. Let it be x1, x2, x3 and x4. So your solution may be 0, 0, 0 and 1, or 1, 0, 0 and 0, or 0, 0, 1, 0 and so on. So just try to observe that the tuple length here is fixed. So this is the fixed tuple size solution or fixed tuple size state space tree generation for solving your uh, sum of subsets problem. So in this class we are going to consider only fixed tuple solutions approach. Okay, so we are going to follow fixed tuple size solution approach. So let us consider a problem instance that is W, or you can say the set containing 6 items and the values of these items are raised. So n is equal to 6 and m means the elements to be summed up only to up to 30 only. Means we need to generate the subsets such that the sum of the elements of that subset is exactly equal to 30. Fine. So this is going to be the problem statement for this instance. And now assume that all the elements are sorted in non-decreasing order. Fine. So they are all in non-decreasing order. Okay. So we started with the root, and there are 3 values at this root. So first value is your 0, then 1, then 70. Now what exactly they mean? Now let us try to define these 3 arguments at this root. So argument number 1, let us call it as S, then argument number 2, call it as K, then argument number 3, call it as R. So S is the sum of elements visited till now. Fine. So this is the sum of the items, or you can say sum of the elements visited till now or till this node. Okay. Now that visit may be having some of the elements excluded and some of the elements included. Now this K is the number of elements, or you can say indices of the elements seen till yet, or you can say that K minus 1 indices are seen till yet or till now, and now we are targeting on the kth item, kth element we are targeting. Fine. Now this R is the sum of the items or sum of the elements which are yet to be explored, So these are 3 arguments. Now to better understand them, consider the root, and we know that at root we have not included any item, so this S becomes equal to 0, and now we are making a check upon the inclusion or exclusion of first element, so put it as equal to 1, and 73 because all the elements of this set are in the non-visited set now, or you can say unexplored now, because we have not yet included any element. So just sum them up. This sums to 73. 5 plus 10 plus 12 plus 13 plus 15 plus 18 comes out to be 73. So it is 73. Means till now we included the items having sum equal to 0. Fine. And the total sum that is left to be visited is equal to 73, and we are going to make a check upon item number 1. Okay, so 1 will be included or 1 will be excluded. Fine. So let us explore the inclusion option. Means when item number 1 was included. If item number 1 was included, then its weight will be as its weight is equal to 5. So we are going to add 5 in the sum of the subset which are processed till now. Okay, and we will go to check for the second item, and the total sum remained in this remained there to be checked is equal to 68. It's very simple. You included the first item, so the sum of the result till now is equal to 5. If 1 is included, now we are going to check for the second item. Okay, and the sum which is yet to be explored is equal to 68. 68 means 73 minus the weight of the first item which was just included. So 73 minus 5 is equal to 68. Now follow this branch. When x1 is equal to 0, it means it was not included. If it was not included, then the sum attained till yet is equal to 0. Okay, and we will be checking for item number 2, and the sum remained in the basket or remained in the set is equal to 68, because now we have already taken the decision about inclusion or exclusion of item number 1. Whatever the result is, the remaining sum is going to be the total sum minus the weight of the first item. Fine. Now we are at this node. So again there will be two options. One, item number 2 is included, then this branch is excluded, then this branch. Now consider this one. So weight of the second element is equal to 10. If it is included, then it will be added to the previous sum which was 5. So 5 plus 10 becomes 15. And now we'll move to check the third item. Okay, and the sum remaining is equal to earlier sum minus weight of the second element, that was 68 minus 10, which is equal to 58. Now consider its exclusion. If it was excluded, it means no addition to the previous sum, means 5 remained 5. Fine, because if item number 2 is not included, then the sum will remain as that of the earlier one. And now we'll go for the check on the third item, and the total weight or total sum remained within the set is equal to 58. Again, I am reiterating that it doesn't matter whether this particular item was included or not included. The thing that matters is that we have seen this item. Okay, if we have seen this item, then the total weight or total sum remained there is to be negated. Fine. Now move to the third item, that is this one for inclusion of this one for exclusion of this. Okay, suppose this is included. If this is included, then the weight of third item is equal to 12, means 12 will be added to 15, will become 27, and we will go for a check on the fourth item, and the weight remained is equal to 46. Fine, and this is the exclusion. So 15 will remain 15, go for the fourth item, and the remaining sum of the set will be equal to 46. Okay, now just try to explore this. Now we are going to make x4 is equal to 1, x4 is equal to 0. If x4 is equal to 1, fine, it means if we add 13, it means it is going to be greater than the total m, that is equal to 30. Yes, no? 27 plus 13 is going to be equal to 40. It means this branch is not to be explored further. Fine. Now consider this case. Here what will be happening here? If we exclude this, if we exclude our fourth item, means this item is excluded, then what will happen? Then what is going to happen is that 13, and this is to be explored, or you can say, you can just label this node as backtrack. Okay, now once again consider its exclusion, means this branch. Now consider that this x4 was excluded, means this is excluded, 13 was not there. So we are having the option later on that we can have 15 there or 18 there. Fine, 15 or 18. So at least 15 is going to be the next weight in the line. So we need to make a check whether current sum that was equal to 27 and immediate next to x of k, which is equal to 15, is it greater than Is it greater than 30? If it is, then we just do not need to explore, or you can say we are going to backtrack from this point. Try to understand this point. We know that our list is already sorted. So if the immediate next element is going to you can say make your total sum greater than m, it means none of the future items is going to be included in the basket. Fine, that is why we need to put a b here, means it will be backtracked. Once these both are backtracked, it means we are going to say that this is backtracked. So we are going to make a single condition considering these two. Fine, we'll study it later. So in the same way, just explore this branch. Once this is explored and till x5 is equal to 1, this results into the solution. And this b is again resulting into the solution. This c is again resulting into the solution. And all other nodes are just, you can say, going to be backtracked. So this is the probable solution for your sum of subsets problem. Now consider this branch also, this node. Okay, this node also. So this node results by putting 0 here, 0 here, 0 here and 0 here. It means first 4 items or first 4 elements were not included into the set. So the sum that is achieved till now is equal to 0, and we are going to make a check upon 5, and the capacity left is equal to 33. Fine. So there will be two branches. One is saying x5 is equal to 1, one is saying x5 is equal to 0. So if x5 is equal to 1, assume that x5 was included, means 15 was included. Then we need to look at the immediate next weight, that is equal to 18. If this sum is going to be greater than m, which is in this case 30, then we are not going to explore this, we need to backtrack. Fine. Now in the second case, when x5 is equal to 0, then we are going to consider that if the sum of future, or you can say the elements to be seen, is greater than m or greater than 30, only then we are going to explore this branch. Now just try to map it to the current case, that if x5 is equal to 0 means 15 was not included, then only one item was remaining, that is equal to 18. Okay, so the sum of the remaining items was not equal to 30 in this case, so this will be again backtracked, and these two backtracked, then this is compulsorily to be backtracked. So next task is to generate the conditions for this backtracking, and the condition for this backtracking I have just taught you earlier also, that they are termed as your bounding functions. They are termed as the bounding function. So the next task in the line is to generate the bounding function. Okay, so let us discuss the bounding function. So what exactly we used to have is, we used to have the b of k considering x1 x2 up to x of k. It may result into true or it may result into falseness. If it is true, then the node is to be explored further. If it is false, then it is going to be shown as the backtracked one. Fine. So consider any intermediate node. Let us pick this one. Fine. So at this particular node, what exactly we are looking at is that if sum of wi and x of I is equal to 1 to k, fine, is equal to m, then we are going to see that print result. Fine, print x. Okay, print x. If this is not true, then we need to make a decision whether this particular node is to be expanded further or not. Now this expansion decision is to be made on two conditions. So condition number one is that if Wixi, where I varies from 1 to k, plus I is equal to k plus 1 to n, if it is greater than or equal to m, only then we need to explore it. Fine. Now what exactly it means, that try to observe. This node, that is, we are going to make a check upon the inclusion of node number 5 or inclusion of item number 5. So this item, so assume that the right path, that is equal to 0, done, means it is excluded. Suppose now once it is excluded, then the previously attained sum, this one, this one, this one, this was 0, this was 0, this was 0, this was 0, so this term is going to become equal to 0. Fine. And the next, or you can say this term, which is equal to, k was equal to 5, so k plus 1 will be equal to 6 to 6, so only one item was left, it is equal to 18. So it is not equal to 30 in this case. That is why there is no scope of generation of any solution by following this node. Why? Because in future the weight, total weight left is less than 30. We just cannot fill even by including all the future weights. So this is the expression for this. The second part of the expression is, which is and, it says that if I is equal to 1 to k Wixi plus W of k plus 1 plus W of k plus 1, if it is less than or equal to m, then only we should follow it, otherwise we need to backtrack. So this is the complete bounding condition for the sum of subsets problem. Now try to have the example of this condition. Consider this node, this one. Consider this node. It says that we are going to make a check whether to explore fourth node or not. Fine. Means this was the path attained till now. So weight was equal to 27 till now, and we are making a check upon the fourth one, and the total remained weight was equal to 46. So two options were there, to include it or to exclude it. Fine. Now try to put it in this equation, that if Wi or Xi, it means it is going to constitute 27 plus next weight, weight of the next item means weight of the fifth item, which is equal to 15. Now it is going to be greater than 30. So this condition is false. And we already know that the weights are in increasing order. So if 15 is not fitting in this condition, it means 18 is not going to fit and all future items are not going to fit into the solution. So that is why we need to make a check upon the next item if inclusion of the next item makes, or you can say keep, your total sum less than, or you can say less than or equal to m. Only then we need to explore it. If this condition is false, then we need to put a backtrack symbol on this. So this in whole constitute the final bounding function. So let us move further in a better way. This is our final bounding function, and within this let us try to name it as a variable s, and this particular term name it as r. R means the remaining weight, remaining sum till to be tested, and s is the sum of the items till now. Fine. And this is the second condition. So these conditions combined as a combination form our bounding function. Okay, so we made the bounding function. Now next term is for our function t, that is generating the future states. So just try to observe that at each node we are generating two children. One was for label 1, one was for label 0. Again, one was for label 1, one was for 0. So t is fixed in this case. T will be left node once and right node second. So 1 for inclusion, 0 for inclusion. So t is fixed for this. Now let us try to write the algorithm for this. Now before writing the algorithm, there are certain assumptions, prerequisites. So what exactly it says is that we wish to have all subsets, not the first one only. We need to all subsets that sums to m, and the value of xj for this already known, means initially x was equal to 0 for all. Okay, so it is talking about at any intermediate stage k. For an intermediate stage k, xj is already known. Fine, have already been determined, and s is equal to this that I just discussed for j is equal to 1 to k minus 1. Fine, so this is the case. Whatever the values were, we need to have the sum of the items included. In the earlier case we took k here, so one and the same thing if k minus 1 is there, and then we need to consider the kth element in the second, that is equal to r. And the next condition is that wj's are in non-decreasing order. Fine, I already discussed. And important conditions that this is true means the weight of the first item is always going to be lesser than or equal to 1. Fine. And the second condition is that the total weight of the subset is always going to be greater than or equal to 1. So these two conditions are prerequisites. This is number 1, this is number 2. Fine. And along with these assumptions, now we can write the algorithm for sum of subsets. What exactly is the algorithm is that name this algorithm as sum of subset. 3 arguments are passed to it, s, k and r, and initial call to this is going to be with 0, 1 and sum that was equal to 73 in our case in the above example. So this is going to be the initial call to this algorithm. Fine. So we need to explore that x1 is equal to 1 or x1 is equal to 0. So this is the case, this one, when xk was initialized to 1. When xk was equal to 1, then we need to check whether we attained the solution. If we attained the solution, then we need to print it. Fine, subset found. If this is false, then we need to go to the else part, and within the else part we need to check the bounding function. Fine, we need to check the bounding function. Now what exactly is the definition for bounding function that I have just conveyed to you? Fine. So it is if the previous sum plus addition of the kth item plus w of k plus 1 is less than equal to m, means the second part, means this part. Okay, this part of your bounding function is checked for this inclusion. Okay, for this inclusion this part is checked. So if it is true, if this is true, then we need to call the sum of subset with these as arguments. Means we need to go further for the next element to check its inclusion or exclusion. So just try to have a look at the arguments. So we included the kth element. Fine. It means we need to add w of k to s, and on the same time we need to subtract w of k from r. Okay, we need to increase the index also, means we need to go for the next node. So this is for the left node, and now right node is yet to be generated. So it is if s plus r minus w of k is greater than m, and s plus w of k plus 1 is less than m. Now these two conditions are again forming two parts of our bounding function, that is b of k. These both are the parts of our b of k. Now to understand how these two are the conditions of your bounding function, try to observe that the variable s and r, what exactly they are giving? They are giving summation of wi and xi. Okay, wi xi, where I is equal to 1 to k plus I is equal to k plus 1 to n and w of I. This is exactly what s plus r mean. Okay, so if your kth item was not included, or k become equal to 0, x of k is equal to 0, then we need to negate or wait for kth element from this. We need to negate the weight of kth element. So this is what exactly it is doing, means s plus r, w of k, means after negating the kth weight, if the condition is still holding, or you can say if even exclusion of kth element, the total remained sum is greater than the total sum to be achieved, only then we need to pursue further. Okay, try to map it with this node, this one. Try to map it to this node, this one. Along with this one. So one out of them is going to satisfy this part number 1, most probably this one. Fine. So this is the condition when we are making sure that if item was excluded, then the total remained sum should be greater than or equal to m. Fine. And the second condition is for the second part of your bounding function, that the current sum plus the immediate element sum should be less than or equal to m. If they are not, then we just cannot have a solution for this. So if these conditions are true, then only we need to expand this kth node in further in two parts, 1 or 0. If any of these conditions is false, then we just are not going to follow this and just are going to label it as backtrack. Fine. Suppose this condition is true, then we need to put a label that xk is equal to 0. Fine. And we need to make a call for the next node. So this is the call for the next node. S remain the same as was the earlier, k plus 1 we move to the next node and we negated its weight from the remainder. Fine. So this is our final algorithm for your sum of subsets problem. Now try to trace it on the example that we discussed above. You will be able to better understand.